Okay, first, we have to calculate the average velocity of water through the pipeline. So for average velocity, you must have Q, you must have a cross-sectional area. Next, estimate the maximum flow rate through the pipe. Okay, maximum flow rate through the pipe. Remember, keywords are very important. Number 3, draw the pump characteristic curve and show the operating point. So there are some things we have to learn. We can learn today. Pump characteristic curve and operating point. Okay? As we go through this exercise, we'll see how a typical pump characteristic curve looks like and what is this operating point. 4, calculate the amount of pressure drop at the operating point. This is a very challenging question. The amount of pressure drop at the operating point. 5, finally, calculate the power of the pump at the operating point. Okay? So, you assume that friction factor due to surface roughness inside the pipe is F is 4.028, and the loss coefficient for the globe bar K is 10, and for each 90 degree bend is 0.9. Okay, so this is actually interesting and challenging question. It opens up our mind to more practical application. So how do we start? The first one, calculate the average velocity of water through this pipeline. Average velocity of this water through the pipeline. How do we start? It's very important in the exam as to how to start. If you don't know how to start, you're just wasting time thinking, you know. So, first one. How can you start? Okay, so we are given that delta P over rho is equal to 10 minus 1000 times Q squared. But we also know another formula for delta P over rho, which we have just learned. That is for the major loss, for major heat loss. We have delta P over rho is friction factor times the pipeline over pipe diameter over the mean flow rate times mean flow rate square over 2. Okay, remember this formula? And we just plug in the values that are given to us. Our friction factor is given as 0.028. In pipeline is given as 50. Okay, meter, so very long time. And the diameter is 0.25 meter. Okay, diameter is 0.25 meter, so 0.25 there. Do we know V squared? Do we know V? We don't know V, right? So V squared, put it back there, over 2. Okay? And this worked out to be 2.8 V squared. Okay? So we have got another equation involving V squared. First one is given, second one, we work it out. Now, next, minor loss. What can we say about minor loss? Minor heat loss. There's another similar expression or formula for delta P over rho, the minor heat loss, which is the loss coefficient K times V squared over 2. Okay? Now, what is this loss coefficient now? Loss coefficient. What's the value of the loss coefficient? Anybody? You have the growth valve, K is 10. And you have 90-degree band, two 90-degree band, okay, with coefficient of 0.9. So the total K will be 10 plus 2 times 0.9. Okay? For the band and the roll bar, there are two bands, so 2 times 0.9. D squared over 2. So here we got another expression involving d squared. So we can find 0.9 d squared. This is a minor loss, related to minor loss. We got a major loss and we got a minor loss. So what's the total loss? Total head loss. Total head loss is major plus minor. So it's 2.8 d squared plus 0.9 d squared, of course. And this gives you 8.7 d squared. That's total head loss. The total head loss is overall delta P over rho. Okay? Overall delta P over rho total. Okay? Delta P over rho total. The first delta P over rho is for major. The second delta P rho is for minor. This delta P is also delta P over rho is the total. Okay? So total loss, so in this case here, the total loss is 8.7 d squared. So therefore, the pump must be able to pump the flow to overcome this total head loss. So we are given that the relationship between the of the pump is expressed as delta P over rho is equal to 10 minus 1000 q squared. So we have 10 minus 1000 q squared. This is the for the pump. The pump must overcome the total. So this is actually a delta P over rho for the pump. Okay? Delta P over rho for the pump over the delta P over rho for the total loss. So it's 8.7 d squared. 1 for equation 1. Okay? There's a total head loss of 8.7 d squared. And the pump must overcome this head loss. And that is 10 minus 1000 q squared. Okay. Yes, there's a Q and there's a D. There's a Q and a V. We cannot find V unless we find Q. So what is Q then? Now, the volumetric flow rate Q is given by A times B. Cross-sectional area times the mean velocity. And of course, cross-sectional area is pi r squared times B. Okay, which is pi over 4. What's the diameter? 0.25 meter. So 0.25 squared times D. So that will give us what? 0.049 D. Okay, so we have managed to set up another equation. So two equations and two unknowns. Right? So now okay. So two equations, two unknowns, you can solve it. Huh? So say from one, substitute one to the other. From 1, 10 minus 1000 q squared is 10 minus 1000. Now what is q squared? From equation 2, q is 0.049 v. So we put that, replace this q with 0.049 v. That will be 0.049 v and it's a square there. Okay, that's good. 8.7 v squared. Now we use only one variable. Okay? So therefore, we can solve. So therefore, D is equal to 0.95 liter per second. That's the first answer. Okay. So not so straightforward to get the first part of the answer. Okay. Now, next part is estimate the maximum flow rate through the pipe. So what's the maximum flow rate through the pipe? So from 2, okay, from graphic part 2, so from equation from 2, what do we have? We have the flow rate Q is 0.049 in velocity. We know the in velocity. Okay, so it's 0.049 times 4.95. So this gives you 0.047 meter cube per second. Okay. So that's the flow rate. Next, the pump characteristic. Wow, pump characteristic. What do you think? How does the pump characteristic look like? You look at any typical book or any typical catalog on the pump characteristic. It always drawn in this form. You have the Q here on the x-axis and the head loss delta P over rho on the y-axis. Okay, and it will go typically at the curve here. You will go like that. Okay? Typical pump characteristic. Okay? And then, what about for the pipe system curve? You have delta P over rho is equal to 8.7 V squared, and V is related to Q. So if you were to plot it out, you will probably end up something like that. Okay? And you have, when they meet, that is your operating point. Operating point. The point where it gets is optimum performance. Means you are when you operate at this point, you are not underutilizing your pump at all. This for this particular pipe system, that is the correct operating point you should operate your pump, so that ensure maximum performance. So you're not wasting energy, you're not undersizing the pump or oversizing the pump. Okay? So that is the right for that system. Your pump operating at that point, that is the correct point, correct operating point. Okay? So again, this is, you can get this from delta P over rho is equals 8.7 V squared. And you convert the V to your Q, you should get a curve. You can do it at home. Okay? You can do it at home. You can put some values here. For example, 10, for example, 0.1, typical value. Okay? And you plot delta P over rho is equal to 8.7 V squared. Convert your V to your Q, you'll get this blue curve. And the given expression, delta P over rho is equal to 10 minus 1000 Q squared will give you this system curve. Okay? We use system curve. The given equation in the question will give you this curve. Alright, that's how this curve is sketched. So that's the pump characteristic curve at the operating point. So the pipe system is a pump. So pipe, pump. Okay, next, calculate the amount of pressure drop at the operating point. Amount of pressure drop at the operating point. So this is the operating point. So the pressure drop, delta P over rho, we got it as equal to 8.7 V squared. Okay, V squared. And here, this is the maximum best performance at this operating point. And here, what is your Q value? Your Q value will correspond with the V. Okay, and we found that that is 8.7. And your V, we found it earlier, is actually 0.95. So it's 7.852. Okay? So that is the pressure head, where the complete pressure drop. Therefore, pressure drop is equal to 7.852 times rho. What is rho? Rho is water. We're using water. It's a water type. So it's 1,000 kilogram per meter cube. So that will give you 7.852 kilopascal. Okay, that's the pressure drop. Okay. And then we have 5 here. 5 says finally calculate the power of the pump at the operating point. So power, the expression for power is S. Okay, here by S is equal to Q times delta P. And this is the expression for pump power. Flow rate times pressure difference. Okay? Q times delta P is the expression for pump power. So we know what Q is 4.047 meter cube per second times your delta P, which is 7.852, and you get an answer as 369 watts. 369 watts. Okay. So that is a very interesting question about the operating point. So now you see the pump characteristic curve. Okay. Pump characteristic curve. So usually that's the pump, that's how it looks like. And this is the pipe system curve. Pipe system curve. Okay. From what we have got here. Okay. So when they do intersect, this is the operating point. This is your pump is operating at that particular flow rate to ensure maximum performance. Okay, so today we've covered, we finished off with topic 8, and we finished off topic 9. Topic 9 also finished. That's very good. So we are done with only one topic, is topic 10, complex pipeline system, which would teach us how to actually calculate flow rate, pressure drop for pipe network. Because so far it's just a single pipe. Okay? Single pipe can go zigzag. It's not a network. So for topic 10, we look at how to do all these calculations involving a pipe network. Okay, next, I hope that you all are doing your tutorial questions. You all should be doing tutorial question 2 already, and try to finish it off, and I will upload tutorial question 3 soon. Okay, so please work on tutorial question 2 on your own as much as possible. So in the next lecture, I'll give you some time to do your tutorials after the lecture. Okay, any questions? Any questions?